Example 4. Using the least amount of material possible, what are the dimensions of a right cylinder with a circular base that holds 1 liter? So what we're basically looking at is a bean can, or a can of soup, or some type of cylindrical shape. It's a right cylinder, so that tells us that it's going to have a right angle where the base of it starts to go up. That's pretty much, again, any soup can that you've seen. We're looking for the least amount of material. So the least amount of material. This means that we're looking for surface area. Well, we need to know our formula for surface area, and the surface area for a cylinder is 2 pi r squared, which represents the top and the bottom circle, plus 2 pi rh. That is the round part of the can on the sides. And we want to use the least amount of material, this means that we want to minimize. So before now we've been maximizing, now we're going to minimize it. It's the same process, but instead of finding a biggest value, we're going to be looking for the smallest. The first thing we need to do is we need to get the surface area in one variable. So we need the surface area in one variable. Right now, it has 2 variables. And they are r and h. Keep in mind that pi is not a variable. It's not a variable. Pi is a number. Pi is about 3.14. So what we need to know then is that 1 liter is equal to 1,000 centimeters cubed. Okay, we're going to use that as a conversion. So because we have 2 variables, we're going to need 2 equations in order to get 1 variable. We know that the formula for surface area is 2 pi r squared plus 2 pi rh. And we actually have a second equation, and that's the volume is equal to pi r squared h. So now that we have 2 equations and 2 variables, we can now substitute to get 1 equation with 1 variable. We know that the volume of this is 1,000. So this is pi r squared h. I'm going to make my equation with r's in it, which means I need to get h isolated here. So I divide both sides by pi r squared. And you get h is equal to 1,000 divided by pi r squared. So what we're going to do is we're going to take this h and plug it back in right there into the surface area formula. So surface area then is 2 pi r squared plus 2 pi r times 1,000 over pi r squared. Now we're going to do a little simplifying and get surface area is equal to 2 pi r squared plus 2,000. The pi's cancel and one of the r's cancel. So 2,000 divided by r. Now this is a very nice formula, nice and easy. So now what we need to do is take the derivative. Now we're going to take our derivative with respect to r. So then we get that our derivative is the derivative of surface area with respect to the radius is going to be 4 pi r plus negative 1 times 2,000 r squared. If you forgot how I did that, this piece right here becomes 2,000 r to the negative 1. So now what we do is we set the derivative equal to 0. You get 4 pi r minus 2,000. Sorry, this is r to the negative 2. R to the negative 2. I'm going to move one of them over to the other side. I get 2,000 divided by r squared equals 4 pi r. Then I'm going to multiply r squared to both sides and get 2,000 is equal to 4 pi r cubed. So I get r cubed is equal to 2,000 divided by 4 pi. So then r is equal to the cube root of 2,000 over 4 pi, which is about 5.42. That means when the cylinder has a radius of 5.42 centimeters, then that means that we are going to have a minimum surface area. Let me visually explain what I mean by this. Here's a cylinder, and here's the radius that I can adjust right here. So what I'm going to do is I'm going to change the radius, and you're going to see this thing change. Remember, the volume stays the same at 1 liter. So if the volume stays the same, that means the dimensions have to change for it to look different. So I'm going to go ahead and I'm going to animate this. And if we look right here, you can see as it gets fatter, it also gets shorter. So it gets short and wide. And then as it gets skinnier, it has to get taller to have the same volume. So as we let the radius get infinitely small, you can see this become infinitely skinny. And at some point, it just takes up a ton of paper. So this graph over here on our left shows the surface area of this. So we said that the surface area is the smallest when r equals 5.42. So let's take this down to 5. And 5.42, whoops, 5.42 is about right here. And this looks like it's at the bottom of the curve. So this is another way to visualize really what's going on with the cylinder changing radius and height. Remember, the radius and the height have a relationship with each other that when one gets bigger, the other has to get smaller to maintain the same volume. So we're pretty much done. I just wanted to show you visually. But what we need to do is to determine if this is a max or if this is a min. Well, in order to do that, you can use the second derivative. So that this is a max or a min. Now remember, the second derivative test will tell you if it's a min. Just by looking at the graph, we were able to see that it is in fact a min. However, let's confirm algebraically. So the derivative of surface area was 4 pi r minus 2,000 r to the negative 2. So if we take the derivative of that, and we get the second derivative, we get 4 pi r, we get 4 pi plus 4,000 r to the negative 3, which is equal to 4 pi plus 4,000 divided by r cubed. Now keep in mind that x is a positive number. So this is always positive. So this means that the second derivative is positive. So x equals 5.42 is a min. Okay, so now we just need to write our summary so we can write off our answer. And we get, remember the question was, given a 1 liter can that uses the least surface area, find the dimensions. So a 1 liter can that uses the least amount of material i.e. has the smallest surface area has the dimensions R equals 5.42 centimeters and H is equal to 10.84 centimeters. And that is your answer.